Welcome to qnawire.
Okay. In this problem, we have a particle approaching a potential bump with height u naught, and we know the relationship between the particle's total energy E and this height of the potential bump. We know that the energy is 3 times that height. We're asked to find the ratio of wavelengths for this particle. When it's in the bump, we'll call that lambda 2, and when it's out of the bump, call it lambda 1. So the only real equation we need to use for this is the de Broglie wavelength definition. So we'll say in our list of equations, you know that lambda is equal to h over momentum of the particle. We can do one more simplification. We can relate momentum to kinetic energy by 2mk. So this is really all we're going to need, but it's kind of nuanced how we use it, a little bit tricky. So taking that de Broglie wavelength, h over root 2m, okay? We can move k over to the other side. So lambda root k is equal to h over root 2m. Now, because we don't expect the mass of this particle to be changing, it's evident that the right-hand side is constant. Thus, the left-hand side also has to be constant, which means this quantity, this product, lambda root k, is constant. Because it's constant in all time, we can say that lambda 1 root k1 is equal to lambda 2 root k2. And this allows us to express a ratio of lambda, of wavelengths, to a ratio of energies, kinetic energies specifically. So all we need to know at this point is what the kinetic energy is in both the different situations. Fortunately, because we're given that E is 3 times the potential, we can then look at each of these situations individually and then find K2 and K1 using just basic energy accounting. So for case 1, where we're not in the potential bump yet, we assume the potential is 0. So the total energy is just K plus mu naught, which means that K is total energy minus mu naught. We assume there's no mu naught, and we know E is 3 times that. So we have 3 mu naught minus 0 equals 3 mu naught. So that's the amount of kinetic energy that this particle has before it enters the bump. Now, when it enters the bump, okay, we'll call that K1. So when it enters the bump, calling it K2, we have total energy minus mu naught, or total energy minus, mu naught. Also cross that out. So, and we plug in our 3 mu naught, and we end up with 2 mu naught. This is the kinetic energy it has when it's in the bump. So from this, we can simply plug it in, and we have lambda 1 over lambda 2 equals root 2 over 3. And that's it.